Hey, can everyone hear me? Okay, cool. We'll get started now then. So welcome to the Math2901 revision seminar. This is a joint collaboration between StatSoc and Mathsoc. Today we'll just be covering the first part of the course, which is centered on probability theory. Just before we start, a bit about me. So I'm Jeffrey. I'm currently a third year student at UNSW. I study advanced maths and computer science, and I major in pure maths and AI. And I'm a director at StatSoc. So yeah, let's get started. Just a quick note regarding the theory. So a lot of the theoretical content was taken directly from Libo's notes, and a lot of the examples were just taken from Rui's slides, and he was a member of the 2018 StatSoc team. Okay. So this is what we'll be covering today in terms of content. I will be looking at some quick theory, some quick probability theory, and then we'll be discussing some random variable properties. Then we'll be looking at the relevant theorems for computing stuff for common distributions. Then we'll look at some inequalities, and then we'll be looking at the relevant results for limits. So this third and fifth point, the computations for common distributions and the limit of random variables, will be like the focus for today. And then after we cover the theory, we'll be just going through lots and lots of examples. So this will be like slightly different to the other revision seminars you might have seen because the way I've structured it is that we'll only be looking at examples after we've quickly gone through the theory. And the idea behind this is that in an exam, they don't tell you like what topic a question belongs to. So it's better that we look at questions in like a vacuum, so we don't know what we should be expecting. So that way we're like forced to try and identify, say like which results are relevant for a particular question. Okay, so let's just get started with the content then. So then we'll be starting off with some basic probability theory. So even though the course is called higher statistics, um, we need a language to talk about like uncertainty, and probability theory gives us that language to talk about uncertainty. Although there is like a bit of a difference between probability theory and statistics. So statistics is like inductive logic. We're going from like results about a sample and then we're trying to make like inferences about the population. It's inductive logic and it's kind of logically unsound, I guess. Whereas probability theory, we're going from like the population and then making like some deductions. And this is like deductive logic, which is sound. And with regards to the probability theory we'll be talking about for now, we're just looking at a few axioms and basic results. Then we'll discuss two important concepts, conditional probability and independence. Then we'll look at a few basic laws, and lastly, we'll finish up with Bayes' formula. Okay, so what is probability theory? So probability theory is about modeling and analyzing random experiments. So random here just means that we don't know the outcome of an experiment in advance. And then to do this modeling in a mathematically rigorous way, we need to specify an appropriate probability space. So this probability space consists of three parts. We have a sample space, omega, which is just a set of all the possible outcomes, and event space F, which is just a set of subsets of omega which satisfy these certain properties. You don't have to worry about this too much. And also, we need a probability function which maps each, say, set of events to a value between 0 and 1. Now, for this like probability function to be meaningful, it should satisfy a few axioms. So this is like, I guess, what mathematicians have found to be the necessary axioms for a probability space to be meaningful. So we need P to map each event to a positive value. We need P to map the sample space to a value of 1. And we also need P to map the union of mutually exclusive events to the sum of the probability of each event. And then as an exercise for the reader, I want you to prove the axioms. Okay, but that was actually a joke because you can't prove the axioms. You just take them for granted. Okay, and then from these axioms, we are able to derive a few of these elementary results, which we can just use without quoting. So the first one, once again, the probability of a sum, or of the union rather, is just the sum of the probabilities. But then this is only the case if the events are mutually exclusive. The probability of the empty set is 0. The probability of any events that's a subset of the sample space is bounded between 0 and 1. The probability of the complement of an event is just 1 minus the probability of the event. And then if B is a subset of A, then the probability of B occurring has to be less than or equal to the probability of A occurring. Okay, so now we'll move on to conditional probability. So conditional probability, the idea is that when we're given certain information, it may change the probability of another event occurring. So a quick example is, say we want to know the probability of a dice rolling a 2. Well, if we don't know anything in advance, we can just say it's a 1 in 6. But if we know in advance that the dice rolled an even number, then we know that it's much more likely that the dice would roll a 2. And then visually, what we're doing when we're conditioning on B is we're restricting ourselves to this B circle, and then the probability of A occurring given that B occurs is like this area divided by this area. And I'm just checking, can you guys see my cursor? So I see a question, so is the stream choppy? I think it's choppy when I try changing between screens to see if there's any questions. So I'll try to change screens less. Okay, and then next concept is the idea of independence. So A and B are independent if the probability of their intersection is just the product of their probabilities. And then another way of thinking about this is that A and B are independent if and only if the probability of A, given that B happened, is still the probability of A. So the way we understand this is that B happening does not affect A happening. Oh wait, you can't see the cursor. Let me try and fix that. Just give me a second. Can you see me highlighting stuff though? Okay, cool. Hang on, I feel like my thing is frozen right now. Just give me a second. Okay, hey, I think we're back now. Can you guys see the screen again? Oh, wait, can you guys like see the slides right now? I think it should be showing now. Okay, cool, you can see it now. Okay, so sorry about that. Let's move on quickly. So with regards to independence, there are two types of independence. There's pairwise independence and mutually independent. And then we don't have to worry about this too much. Just know that mutually independence implies pairwise independence, but not the other way around. Okay, so let's move on to some laws. So we have the multiplicative law, which gives us a way of calculating the conjunction of events occurring. So if we want to know the probability of A1 and A2 occurring, it's A1 probability of A1 occurring, and then the probability of A2 occurring given that A1 occurred. And then this generalizes to, say, the free event case. So if we want the probability of three events occurring, it's the probability of the first event occurring, and then the probability of the second event occurring, given that the first event occurred, and then the probability of the third event occurring, given that the other two have already occurred. And of course, this will generalize to a greater number of events. And you would use this when dealing with a sequence of dependent trials. So for example, if you're like drawing cards from a deck without replacement, then the second card that you draw will depend on the first card that you draw. So for example, if you draw like a three of hearts on the first card, then you can't draw a three of hearts on the second card. Next, we have the additive law. So what the additive law does, it gives us a way of calculating the probability of a disjunction of events. So if we have two events A and B, and we want to calculate the probability of, say, either of them occurring, it's the probability of each one occurring, and then we take out the probability of both of them occurring because this gets counted twice. And of course, this also generalizes to a greater number of events. And what you might notice is that this is actually quite similar in form to the inclusion-exclusion principle. And then I have a quote here from Wikipedia which sheds some light on this. So as finite probabilities are computed as counts relative to the cardinality of the probability space, the formulas for the principle of inclusion-exclusion remain valid when the cardinalities of these sets are replaced by finite probabilities. So that's just something to think about, I guess. That's interesting. Okay, and then we have the law of total probability. So this will be used when we're looking at Bayes' formula. The idea is that if we have a partition of the sample space, so by partition I mean that each event is mutually exclusive in the sense that they have no overlap, and they're exhaustive in the sense that their union forms the entire sample space, then for any event B, we have this formula for calculating B. So given the conditional probabilities of B, we are able to calculate the marginal probability of B. And then what the law of total probability does is it gives us a way of calculating PB, which you'll see often in Bayes' formula or Bayes' theorem or Bayes' law. And what Bayes' theorem is, it's a way of um, allowing us to reverse the order of conditioning. So say we know PB given A, but what we're really interested in is PA given B. And if we know these certain other quantities, so if we know PA and PB, then Bayes' theorem allows us to calculate this quantity PA given B. And then there's a lot more to like Bayes' theorem and like what it actually means. So I guess if you're more interested in this kind of stuff, you can like look into, say, the Bayesian interpretation rather than the frequentist interpretation. Okay, so that was the probability theory. Let's just quickly go through some random variable stuff now. So recall that we have two different types of random variables, discrete random variables and continuous random variables. So a random variable is discrete if there are countably many values for which the probability is positive for. So countably many here does not necessarily mean finite. So countably many within maths means the cardinality is equal to that of a subset of the natural numbers. So it could be finite, but then there are also certain like infinitely many values for x. Okay, and then to describe the probability structure of x, then what we often look at is its probability function. So the probability function written fx is just the probability that x takes on a particular value. And of course, fx has a few properties. So we know that fx has to be positive, or not positive, it has to be non-negative for all x and r. And we know that the sum of all the probability functions for the different x values has to equal to 1 exactly. And then, of course, we also have a continuous random variable. So as opposed to the discrete random variable, the continuous random variable has a continuum of possible values. And then what you'll notice is that rather than a sum, what we have instead is an integral. And this kind of makes sense if you think about it, because an integral is like, it's sort of a sum. Okay, and notice that its properties, it has like the same properties essentially. We know that each fx has to be non-negative, and we know that the integral of all the fx's have to equal to 1. Okay, so that was we've looked at the probability function for the discrete random variable case and the probability density function for the continuous random variable case. And then what we can do now is we can look at this idea of the CDF, the cumulative distribution function. So what the CDF gives us is a way of calculating the probability of the random variable taking on all values less than or equal to a particular random variable. And we see that the CDF has a few properties. And these properties here is just for when x is continuous. And then the thing is, if we know big fx or little fx, then we can derive the other one and pretty much get anything we want regarding a particular random variable. And someone asked if it's recorded. Yes, I think like it's automatically like recorded and like hosted on Twitch for 2 weeks. Okay, and now just a quick remark on continuous random variables. So for a continuous random variable, the probability that x takes on a specific value is equal to 0. I think a bit more generally, the probability of x being in a subset of measures 0 is just equal to 0. And within continuous random variables, it's only meaningful to talk about x lying in some subinterval. And then another consequence of this is that it doesn't matter if we're looking at strict inequalities or not when we're talking about continuous random variables. But note that this is not the case for discrete random variables. Okay, next, now we're looking at expectation. So expectation can just be thought of as the weighted sum. So we're adding up each possible outcome and then weighted by its probability of occurring. And in the continuous case, it's very similar. So we're just summing up or integrating over all the possible outcomes and the corresponding probability of each outcome. And then if we want so sometimes we're not just interested in, say, the expectation of a random variable, maybe we're interested in a transformation of it. So for example, if the only random variable we know is, say, the side length of a square, but the random variable we want to know is, say, the area of a square, then we might be interested in, say, like the expectation of x squared. And then to calculate that, it's still like the same idea. So we take the value of the outcome, in this case it's gx, and then we weigh it by its probability of occurring, which is still fx. And that's the same idea in the continuous case. Okay, and then just some quick properties of expectation. So expectation is linear. So if you've studied like linear algebra before, what we mean by linear is that we can like say separate it like this. So the expectation of the sum is the sum of the expectation, and also we can like move constant multiplicative factors outside or inside the expectation operator as however we want. And then the expectation of a constant is just a constant. And then what we have to be careful of though is that if x and y are dependent, then the expectation of the product is not the product of the expectations. And in addition, if we have a transformation, then the expectation of the transformation is typically not the transformation of the expectation. So hopefully that makes sense. So next up we have variance. So what variance looks at is how, like, say, a random variable deviates about its mean, and it has this formula here. So this is like the definition of variance, but what we'll see later is an alternative way of calculating variance. So you see that it's the expectation of how much x moves about its mean and then squared. And then standard deviation. So the standard deviation has the same unit as the random variable of interest. So these are more like interpretable. But variance has like nicer mathematical properties, so you'll often be working with variance instead of the standard deviation. Okay, and then as I mentioned earlier, for variance, we do have this alternative formula. So variance of x is just the expectation of x squared minus the mean squared, I guess. And then unlike expectation, variance is nonlinear, but it does have these properties. So if we add a constant to a random variable, it doesn't change the variance, which makes sense, right? But then if we multiply our random variable by a constant a, then the variance will be multiplied by a factor of a squared. Okay, and then lastly, for now, we'll be looking at the moment generating function. So the moment generating function has this formula. So it's just the expectation of e to the power of u times our random variable. And the reason it's called the moment generating function is because we have this relationship between the moments of x and the half derivative of the moment generating function. But then this is like not the only way we're going to be using it though, because the moment generating function also has two more properties which makes it really useful. So first of all, the moment generating function of a random variable is unique. So given a moment generating function, there's only one associated random variable and vice versa. And the next property, which will be useful later, is that the convergence of moment generating functions implies the convergence of the CDFs. And this will be useful later when we're looking at the convergence or when we're proving results regarding convergence. And then as a last note, what you often notice is that these like probability functions and density functions, some of them will be quite similar, and the only difference is that they're either like shifted or scaled a bit. And then we'll look at this more generally later on, but this like relates to the concept of parameters in statistics. And in general, if you notice that, say a probability density function belongs to a particular family, then you can like make use of known results about that family of distributions in your calculations. Okay, so next up, we'll move on to the relevant theory for computing stuff with regards to common distributions. Any questions so far? Just drop your questions in the chat. Okay, if there's no questions, we'll just keep moving on for now then. Yep, so for this part of the course, we'll be looking at a few things. So first of all, we're going to be looking at the relevant results for joint distributions, in particular bivariate distributions. And then we'll be looking at the relevant theory for computing the sum of random variables, namely using the convolution formula, the bivariate transforms, and the moment generating functions. And then another thing we'll be looking at is how to identify distributions from the moment generating function. So recall that we're only quickly covering the theory here. We'll be looking at more specific examples at the end. So first we're going to be looking at are some common distributions. So remember, you don't have to memorize these results since I believe you have an open book exam. But first thing we'll be looking at is the Bernoulli distribution, which just measures if an event succeeds in a success or failure. And then we have the binomial distribution, which counts the number of successes given n trials. So someone asks, what do I mean by marginal probability? So the marginal probability is just the probability of an event. Okay, so for example, the probability of x given a. And then this is opposed to the conditional probability, for example, the probability of x equaling to a given that b occurred. Does that make sense? Okay, hopefully that made sense. So marginal probability just means that it's just probability of x equaling a, and then this is opposed to the conditional probability of x equaling to a, say given that event b has occurred. Okay, cool. Let's move on then. So that was the binomial distribution. Next up we have the geometric distribution, which is quite similar, except we're looking at the number of trials until the first success occurs. And just quickly, if you look at its formula, the probability function formula, so remember, P here is the probability of success. So we need to fail x minus 1 times and then succeed on the x try. So once again, like these formulas, you can just check them during the exam, right? Because I think it's pretty much open book for you guys. And then we have the Poisson distribution. So this models the occurrence of point events in a continuum. So an example we'll be looking at later is like the number of like phone calls occurring in some time period. And then we have the exponential distribution. And then this again is like similar, except it models, this is like similar to the geometric distribution in that it models the time until the first event can occur. And then what's special about the exponential distribution is that it has this memoryless property in the sense that, say like some time has passed, it doesn't affect like, so the memoryless property, like it just means that the more like time passing doesn't affect the probability. Okay, and then we have like the uniform distribution where the random variable can take on any value in a certain interval with equal probability. Okay, and then these next few functions, they're not distributions. These are just functions which will be helpful in us like understanding the distributions we're about to look at. So we have the gamma function, which can be seen to extend the factorial function to the real numbers. So of course there are many ways of extending the factorial function to the real numbers, but I guess the gamma function does this in a nice and smooth way. One thing you need to watch out for though is that gamma of n is n minus 1 factorial rather than n factorial. Next we have the beta function, which is closely related to the gamma function, and it has this form. And lastly, we have the phi function. So, of course, this one will be used when we're looking at the normal distribution. Okay, so the normal distribution is probably one of the most like important distributions that you'll be looking at. So it has this formula. So it does seem quite complicated, but something to note is that it is symmetric about its mean, and then it's just like being scaled here and here. And then, oh yeah, so I should have like noticed earlier, notice that we use this like squiggly line here. And the way we read this in this case is that x is distributed as a normal function with mean mu and variation sigma squared, with variance sigma squared. So yeah, this symbol here just means is distributed as or has the distribution. Okay, and then if we have so n01, so a normal distribution with mean 0 and variance 1 is what we call a standard normal distribution. And then the way we calculate probabilities for the standard normal distribution is we just map the corresponding x value using the phi function. So if we look back at the phi function, what we said here is that there is no closed form antiderivative. So you can't actually like just plug in the relevant x value and then evaluate it. What you'll be doing is you have like a table of values, and then after you have the x value of interest, you'll just look up the table of values and get an approximation. And then a really useful result for dealing with more general normal distributions is that we can transform any normal distribution into the standard normal distribution by normalizing it, by just subtracting its mean and dividing by the standard deviation. And then once we have the transformation, we can just use this result to do any calculations of interest. Okay, so these next two distributions won't be too important, I guess. You probably won't see these, but it's just good to know. We have the gamma distribution, which can be seen to generalize the exponential distribution and has this lovely formula here. And then we also have the beta distribution, which can be seen to generalize the uniform distribution, and it has this lovely formula here. Okay, so that was it for distributions. Now let's just quickly look at joint functions. So, marginal distributions are nice to work with. So say the probability of just say x equaling some value. But in reality, many phenomena that we deal with, it can't just be modeled by a single marginal distribution. Rather, it's modeled by a joint probability function, or a joint distribution rather. So the formulas I'll be looking at will be quite similar to the marginal formulas, but then we'll see that there's some other stuff that we have to consider. So first of all, we have the joint probability function. So this is the discrete case, and when we say fxy, it's just the probability of x equaling to x and y equaling to y. And note that to evaluate this, it's not just the probability of x equaling to x times the probability of y equaling to y, unless they're independent. In the discrete case then, usually what you will have, the question will give you a table of values, and then you look at the relevant table to calculate probabilities. Okay, and then in the continuous case, what we have instead is this double integral. And then what this double integral gives us is the probability of x and y being in a certain subset of R2. Okay, and then to generalize the concept of the CDF to the joint case, all we have is this. So fxy is just the probability of x being less than or equal to x and y being less than or equal to y, which has this formula in the discrete case and this formula in the continuous case. And then we know that if we sum up all the possible x and y's or integrate over all of R2, then we know that it should equal to 1. And then we have the expectation of joint functions. So notice that it's really similar. The only difference right now is that we're considering all x's and all y's, whereas before in the single variable case, it was just the x's or just the y's. Okay, and then marginal probability function. Okay, so this next part is very important. So this is how we go between a joint function and a marginal function. So so then to go from this marginal function to just say the marginal function, to go from this joint function to the marginal function just in terms of x, what we do is we sum up over all the y's. And then similarly, to go from the joint function to just the marginal function of y, we sum up over all the x's. And then it's very similar for the continuous case. So then we integrate over all the possible values of y and integrate over all the possible values of x. Okay, and then so that was joint functions. The next thing we'll be looking at are conditional functions. So conditional is actually a lot easier to deal with than joint functions, because what you'll notice is that for conditional, it's pretty much just marginal, because once we've conditioned on y, then what we get is essentially just a marginal distribution. So what I mean by that is, in the following formulas, if you just disregard the y part, then we'll just get back the original results for marginal functions. Okay, and then same idea. So for discrete and continuous, it's the same idea. So for example, over here, right? If we ignore the conditioning part, so just ignore this y part, then we just get the expectation for a discrete random variable x. So once you've conditioned, what you get is a single random variable pretty much. Okay, and then now that we've looked at joint distributions and conditional distributions, what we can do now is like generalize our understanding of independence. So then we can say that x and y are independent then if their joint distribution is equal to the product of their marginal distributions. And another way of thinking about it is that x and y are independent if the conditional distribution is just equal to, say, the marginal distribution. Okay, and then we'll be looking at covariance and correlation next. So real quickly, so covariance has this formula. So it's just the expectation of the difference between x and its mean and y and its mean. And it just measures how much x and y vary about their means and how much they vary together linearly. And then of course covariance has these properties. In particular, I think we'll be using this one later on for some calculations. And of course, if two random variables are independent, then there is no covariance between them. Correlation, it's kind of similar to covariance, except we're dividing out by the standard deviations, or rather by the square root of the product of the variances, and then it has these properties. And similarly, it just measures the strength of linear association between x and y. Okay, so this next part, transformations. So for the discrete case, what we do is, if y is a transformation of x, so y is equal to hx, then to calculate the probability function of y, we just do the reverse mapping. So the probability of y equaling to y is the probability of hx equaling to y, which is equal to the probability of x equaling to x, but then we sum over all the x's such that hx is equal to y. And I believe this should be a lowercase x actually. And then for the continuous case though, notice that we can't just perform the reverse mapping straight away. We also have this like extra factor here, this dx dy factor, which we can think of as like a normalizing factor, such that when we integrate fy, we do get a value of 1 when we integrate over all of r. And then of course, then we'll be looking at examples of this later. And then this is just a simple case. This is like a linear transformation. So notice that we have the reverse mapping, I guess, and then we have this normalization factor. And then leading into bivariate transformations now. So this is one way of approaching it. So if x and y have a joint density of fxy, and u is a function of x and y, we can find the density of u by calculating, the CDF and then differentiating. But then what you'll find is that in the bivariate case, you'll be dealing with like a double integral, and we don't really want to do that. So what we do instead is we have a few different alternative methods. Okay, so this first method, or this first thing we're looking at is called the bivariate transformation. And what we're doing is to go from x and y into u and v, what we do is we have to multiply our original density function by the determinant of the Jacobian. So the Jacobian refers to this, and just be careful about the relative positions of the x and y's and u's and v's. So in the rows, it's dx, and then dy, and then like in the columns, it's u and u, and then v and v. So just be careful of that. Okay, and then to find the, say, the new marginal distribution, the marginal density function by the bivariate transformation, first we define some transformation, then we calculate the joint one, and then we find the marginal by, say, integrating over the other random variable. Okay, and remember, we'll be looking at examples of this at the end. Okay, and then so now we'll be looking at a way of calculating the sum of independent random variables, and then there are a few different approaches which we'll be looking at. So we'll be looking at the probability function, and the density function approach. Later on, we'll be looking at the moment generating function approach. So really quickly, so this is the convolution formula here. So then, In this case, we're just looking at the sum of two random variables. So just say z, which is equal to the sum of x and y. And then I guess the convolution formula, the way you can think about it is, it's a way of like blending the two distributions of x and y to give the correct distribution for z. And I believe this should be a z here. So yeah, that should be a z here. So be careful. Don't use my notes as a reference for the formulas actually. Anyway, notice that x and y, this could be, we could sub this of y, this of x, and then this of x, and this of x. It doesn't really matter. Okay, and then just a quick result. So then the sum of x's, if they're all distributed as gamma functions, is also a gamma function with these parameters. And then an alternative approach to looking at the sum of random variables is by looking at the moment generating function approach. Because remember from earlier, I said that the moment generating function uniquely defines a random variable. So if we're interested in the distribution of z equals x plus y, we have this result here. So the moment generating function of x plus y is the product of the moment generating function of each one. And as a useful result is that the sum of normal distributions is still a normal distribution, but with these parameters. And both these results are generalized to the, say, multivariable case. Also remember, if you have any questions, feel free to drop them in the chat and I'll have a look at them. No questions? Okay, we'll move on then. Okay, so next up, we'll be looking at free inequalities that might be useful, might not be. I personally don't recall using these in the final exam, but maybe they might be useful this year. So we have Jensen's inequality, and pretty much what it says is if h is a convex function, so it just means like concave up, so think of a parabola for instance, then the expectation of the transformation is greater than or equal to the transformation of the expectation. So remember earlier, we had that result saying that the expectation of a transformation is in general not equal to the transformation of the expectation. And in this case, if h is convex, then we know that the expectation of the transformation is greater than the transformation of the expectation. And then we also have Markov's inequality. So something useful about Markov's inequality and Chebyshev's inequality is that there isn't really a restriction on x. So notice that here x is any non-negative random variable. So as long as x is any non-negative random variable, then the probability that x is at least a is at most the expectation of x divided by a. And then if we're looking at Chebyshev's inequality, the probability that x is more than k standard deviations from its mean is less than or equal to this 1 on k squared. And then actually Chebyshev's inequality can easily be derived from Markov's inequality. So if you look at these two, they are actually quite similar. And then as a hint, if you want to do it yourself, just consider this random variable. Okay, next up. So last bit of theory that we'll cover before we dive right into the examples. Okay, so this next part is on the limit of random variables. And I guess this would be like the most like theoretically complicated part of the probability theory section. So we'll be talking about the 3 modes of convergence that you probably need to know. So I know that in the notes there's like all these different modes of convergence, but I believe that these 3 are the most important ones. Then we'll be looking at the central limit theorem. Then we'll be looking at the strong and weak law of large numbers, and then we'll be looking at the delta method. Okay, so almost sure convergence. So what almost sure convergence is, it's saying that an event is, so just a bit of context, an event in probability theory is said to happen almost surely if it happens with probability 1. Now that might seem like kind of like a redundant definition, right? Because why do we have to say this? Well, because remember that in the continuous case, it is possible for these set of exceptions to be non-empty as long as there's probability 0. So there may be like a few, there might be like a finite set of exceptions, but in the continuous random variable case, any finite set has measure 0. And then this is the definition, but when we're dealing with questions involving almost sure convergence, we often use this formula instead. Now, this honestly probably looks like just as complicated, but I think what we'll see is that this is more workable than this formula. And then just for context, almost sure convergence is the mode of convergence used in the strong law of large numbers. So I guess the main takeaway right now, what I want you to understand is like how to interpret each of these in an intuitive way. So almost sure convergence just means that it's pretty much guaranteed to happen. Okay, and then a slightly weaker mode of convergence is convergence in probability. Okay, and then the idea of convergence in probability is that the probability of an unusual event becomes smaller as the sequence progresses. So notice that what we're saying here is that as n approaches infinity, the probability of x being x being greater than of xn being greater than x by some amount epsilon is equal to 0. And then for context, this is the mode of convergence used in establishing the weak law of large numbers. And then almost sure convergence and convergence in probability has this relationship. So almost sure convergence is a stronger mode of convergence than convergence in probability, as it implies it and not the other way around. And then we have this other result. So if something almost surely converges to 0, then the supremum of xk converges in probability to 0. And then I guess an intuitive way of understanding why almost sure convergence is stronger than convergence in probability is that almost sure convergence depends on a joint distribution, whereas convergence in probability only depends on a marginal distribution. And then I have these like wise words of wisdom here for you guys. So there's this diagram in the notes of like these like noodles, I guess. It's not really noodles, it's like these graphs being bounded between these two intervals. But then what almost sure convergence guarantees is that no noodle leaves the strip for large enough n, whereas convergence in probability means that the proportion of noodles leaving the strip goes to 0. Okay, and lastly, we have convergence in distribution. So this is the weakest mode of convergence out of the 3 modes of convergence. And let's just see what it's about. So convergence in distribution is concerned with whether the distributions of this sequence converges to the distribution of some random variable x. So then an intuitive way of understanding this is that we increasingly expect to see the next outcome in a sequence of random experiments become better modeled by a given probability distribution. So in other words, the limit as n approaches infinity of xn is just the fx of the random variable of interest. So in this case, we say that fx is the limiting distribution of the sequence xn. And then where you'll see convergence in distribution is in the central limit theorem. Okay, and then let me just say, is this useful? Yeah. So what this is saying, remember we saw earlier that second result about the moment generating function, how the convergence of moment generating functions implies the convergence of the CDFs. So that's what's being said here. And as we said earlier, convergence in distribution is the weakest mode of convergence, and convergence in the probability implies it. And then what the difference between these two is that convergence and probability is concerned with the convergence of the actual values, whereas convergence in distribution is concerned with the convergence of the distributions. Okay, next up, we're looking at the law of large numbers. So we have the weak law of large numbers, later on we'll be looking at the strong law of large numbers. So the idea is that if we have a group of independent random variables, each with mean mu and variance sigma squared, then we have this result. So the sample converges in probability to the average. We have Slutsky's theorem, but I don't think this will be that useful for you guys. I guess it's just something to keep in mind for now. And then we have the strong law of large numbers, which is all said earlier, except in this case we have almost sure convergence. Okay, central limit theorem. So this will be useful. So if we have a group of random variables which are independent and identically distributed with a common mean and a common variance, then once we normalize it, the probability distribution will approach the standard normal distribution. And of course, there are like several ways of formulating the central limit theorem. So these are some like common ways of formulating it. In each case, the main idea is that the sum of these IIDs converges in distribution to a normal distribution. And then we see here some way how we can apply this for some common distributions. So for the, say, the binomial distribution in this case, x minus np, so this is the mean and this is the standard, this is the variant, the standard deviation, since it's taking the square root, converges in distribution to the normal distribution. And then I think in the notes you might have looked at the continuity correction. And then in general, if you want to make a continuity correction, since these are discrete random variables and the normal distribution is a continuous random variable, what you do is you just add half to the numerator. Okay, and then last thing before we look at some examples is the delta method. So the delta method is a way of analyzing the transformation of a sequence of random variables. So we'll be looking at an example later, because this might look kind of complicated, but when we look at the example for the delta method question, we'll see that this isn't actually too hard. Any questions before we dive into the examples? Okay, if there are no questions, I guess we'll get started then. So just quickly, some tips. Sorry, some tips. So when you're finding a PDF or a CDF, what you always want to do is you want to specify the domain over which it is defined. If you don't do it, then you're very likely going to lose some marks. And then before applying any like result, theorem, or property, make sure that the relevant conditions are satisfied. So for example, if the result requires the random variables to be IID, make sure that... Okay, so someone asked, what was that about adding half for the discrete case? So if we go back to here, so the idea of adding half, it's called the continuity correction. It's because the binomial distribution and the Poisson distribution, they're both discrete random variables, whereas the normal distribution is a continuous random variable. So obviously you can't like precisely approximate a discrete random variable by a continuous random variable. So this is a pretty good approximation, but if you want it to be a more precise approximation, then you would add half to the numerator. Does that make sense? I think in general, you don't have to worry. Yeah, okay, cool. In general, you don't have to worry about it too much unless the question specifically asks for it. Because if you like don't do this and the question doesn't ask for it, then I guess it's not too much to worry about. Okay, so pretty much before you apply some result or theorem, make sure the relevant conditions are satisfied. So for example, are they IID? And does the sequence of random variables, for example, have the right mode of convergence? Because remember, the weak law of large numbers needs convergence in probability, whereas the strong law requires almost sure convergence. Another thing to watch out for is, does the PDF in question belong to a known family? Because if so, you can typically make use of some known results. And another thing I guess you want to be good at is like identifying the corresponding family from the PDF or from the MGF. Because I think later on we'll see a question where you had to be able to identify the relevant family directly from the MGF. Next tip, just make sure you know the the relative strengths, or the relative the relative strengths of the modes of convergence. So almost sure convergence is the strongest, followed by convergence and probability, followed by convergence and distribution. And in terms of like what you actually need to know, I would like break it down to these 4 points. You need to know how to do calculations involving bivariate distributions and bivariate transformations. You need to know how to sum independent random variables using the convolution formula approach and the moment generating function approach. And lastly, you need to know those relevant results for limits and know how to apply them. Okay, actually, I think we'll take a quick 1 minute, like 2 minute break before we get started on the first example. In the meantime, if anyone has any questions, feel free to ask. I'll be right back. Alright, so let's just get started on the examples. So remember, the reason we put all the examples at the end is because if I put theory example, then you'll know, you already know like which results you'll be using to solve the example. But in an exam, they don't do that, right? In an exam, they don't tell you, oh, this question belongs to this topic, so you should use results from that topic. So by putting the questions like in this format, we're forced to figure out which topic a question belongs to, and by extension, which results we should be thinking about using. So someone asked, are the slides going to be posted? Yeah, we'll be posting these slides afterwards. Okay, so let's look at this first example. So, so this is just taken from like first year maths, but what it does demonstrate is like how to apply Bayes' formula. So 99% of the people with the disease receive a positive test. 98% of those without the disease receive a negative test. If 2% of the population have the disease, determine the probability of someone having the disease given that they receive a positive test. So this value here, 99%, within the context of like medical diagnosis, it's what's known as the sensitivity, whereas this 98% is known as the specificity. So then in this question, we're given the sensitivity, so the probability of them having the disease, given that they tested positive, but what we want to know is them having the disease, given that they received a positive test. And then in practice, I guess this is like the more useful result, right? We want to know the probability of someone actually having the disease, given that they tested positive. So to do this, since we're reversing the order of conditioning, we have to apply a Bayes formula. And then to do so, we know PET given D, right? That was just 0.99. And we know PD, the probability of disease, right? That was just 0.02. And then to calculate the probability of T, so the probability of them testing positive, we use the law of total probability. Because the probability of someone testing positive is just the probability of them testing positive given that they have the disease, and then the probability of like them testing positive given that they don't have the disease. And then using the law of total probability and the method and like the idea of a complement, we can calculate it as so. And then our final answer should be roughly half. So I guess that's interesting then, is that even though we have like all these 99%, these 98%, the probability of someone actually having the disease, given that they received the positive test, is only around half. Okay, and then I guess like a quick tip with regards to Bayes' laws, if you're like stuck, use a tree diagram. This next result, oops. So given the distribution of x below, compute its expectation and standard deviation. So recall, to recompute the expectation, it's just the sum of all the possible outputs weighted by the probabilities. So that's what we have here. And then to compute the standard deviation next, what we do is we first calculate the expectation of x squared. And then recall that to calculate the expectation of a transformation, we just like transform the appropriate outcomes or the appropriate outputs, but then the weight is still the same. Yep, and then recall that the standard deviation formula is just the square root of ex squared minus ex squared, and then it's just this. Okay, this next one will be slightly more useful, or more like directly relevant to your upcoming exam, because this is just a warm-up, I guess. So if this has a geometric distribution with parameter p, prove that the expected value of x is equal to 1 over p. Okay, so recall that for a geometric distribution, the probability function has this formula, because we want to fail x minus 1 times before we succeed on the x time. So then the expected value is just the outcome multiplied by the probability, and then subbing in the formula for the probability, we have this. And then, okay, so let's see what just happened here. To go from this first line to the second line, what we do is we make this substitution y is equal to x minus 1. And then after we do that, what we do is we take out a factor of 1 minus p. So the reason why we do all of this will be apparent in a second. Okay, and then within the sum, we split up the y plus 1 to obtain these two separate sums. And then from here, we can evaluate at 0. So we like take out the y equals 0 part. So in this case, at y is equal to 0, we have 0, so this part doesn't change. At this part, at y is equal to 0, we have this p 1 minus p to the negative 1 factor, which we just take out. And notice that now both these sums begin at y is equal to 1. Now, what was the point of this? Well, notice that this part here, right, yp 1 minus p to the power of y minus 1 is exactly the same as this part here. The only difference is that we have it in terms of y rather than x, but that's just a dummy variable. So what we can do then is we can replace this with ex. Okay, and then this other part here, this is just a GP, right? And then using the sum of a GP formula, we have this. Okay, and then rearranging then, if we rearrange to get the ex's on one side, we end up with this. And then finally, we get this. So I guess like doing this like splitting thing and then obtaining the original expression again, it's a common trick that you will need to know. And then in general, these types of questions, they can be done with a Taylor series or the binomial theorem, but I think you might often have to use the technique that we just did, which is like try to bring back ex and then rearrange. Any questions about that example? Okay, cool. We'll move on then. So this next example, given this PDF, compute the moment generating function and assert its existence. So if you recall, the moment generating function has the formula, so it's just the expected value of e to the value of u times x. And then for the continuous case, the expectation is calculated by the appropriate integral. And then to integrate x times e to the ux, we have to use integration by parts. And then, so just integrating by parts, we get this thingy here. So this here is the moment generating function. But this next part, we have to assert its existence. Because recall that the moment generating function, we often evaluate it at u equals 0. But if we just sub in u is equal to 0 here, notice that the bottom will equal to 0. On the other hand, the top will equal to 0 too. So then what this suggests is that we should use L'Hopital's formula to evaluate this limit. And then using L'Hopital's, we verify that indeed the limit of this as u approaches 0 is equal to 1. So the limit is finite, and thus the MGF exists. Any questions about that? Okay. Okay, next part. So now we're using the MGF of this random variable to find the first moment, the expectation. So then recall that the rth moment of a random variable is equal to the rth derivative of the moment generating function evaluated at 0. So then taking the limit as u approaches 0, so the moment generating function of, so where did we get this from? So this is just the moment generating function for a binomial distribution. And then this is like given. So we can just like take this for granted, and then we're just taking the limit as u approaches 0 here, and then we get this. So there's not too much to it. So this next example, a busy switchboard deals with 150 calls an hour on average. Assume that every call is independent and can be modeled with a Poisson distribution. Find the probability of exactly 3 calls in a given minute and at least 10 calls in a given 5-minute period. So the idea is that the good thing about the Poisson distribution is that we can easily scale it to be in terms of the relevant time period. So even though the question gives us 150 calls per hour, we can easily scale it to, say, a Poisson with parameter 2.5, and that just says 2.5 calls per minute. And then to calculate the probability of 3 calls in a minute, we just look at probability of x equaling 3, and that's just subbing in 3 into the appropriate probability function, and then we get this value. Okay, and this next one's a slightly more tricky. So then first of all, which we want at least 10 calls in a 5-minute period. So we scale the time period by multiplying the previous Poisson parameter by 5. And then to get the probability of y being greater than or equal to 10, what we do is we take the complement. And then taking the complement and then plugging in the relevant probability function and evaluating it at the relevant points, we get this expression. And then you'll just enter this into your calculator. So hopefully in your actual exam you won't get something this tedious, because there are like 9 different terms here. But then I guess you could just use R and then get the exact value, or not the exact value, or you can just evaluate it a lot quicker. Okay, and then next example. So if on average 5 servers go offline during the day, what is the chance that no servers will go offline in the next hour? So this random variable can be modeled as a Poisson 5, but what we're really interested in is the corresponding exponential distribution, right? And then what we're interested from there is the probability that t is greater than or equal to or greater than 1 over 24, because recall that this is measured in terms of day right now. And then just evaluating it, we have this, so 1 over 24. Okay, this next part. So now we're given the distribution of a discrete random variable, and what we're interested in is the corresponding distribution of certain transformations. So we're looking at the cube of the random variable and the square of the random variable. Okay, so x takes on these values with these probabilities. So then y cubed, or rather x cubed, takes on these values, right, the corresponding value cubed, with the same probabilities as before. So the probability, for example, right, the probability of y equaling to -1 is just the probability of x cubed equaling to -1, which is equal to the probability of x equaling to -1, which is just 0.38. And the same idea for the other values. For the x squared case, though, this is a bit different, because For example, right, the probability of x cubed equaling to 1 is equal to the probability of x equaling to 1 or minus 1. So in this case, the probability of z equaling to 1 is 0.38 plus 0.14, which is equal to 0.62. But however, the probability of z equaling to 4 is just this squared. And then for another example, right, if we have a Poisson distribution, notice that the corresponding parameter of y, which is x squared, is just square root of y. And then notice that y in this case can only take on square values, because the Poisson distribution, it wouldn't, it's not defined for non-integer values. So notice that in these two cases that we just looked at, the relevant random variables were all discrete. So in this case, we just performed like the reverse mapping straight away. But then in the continuous case, we have to multiply by this like normalizing factor. So let's look at an example. So if we have x being distributed as an exponential distribution with parameter lambda, let's calculate the density of y, which is equal to x squared. So looking back at this formula, right, we need, so h is just equal to x squared. And the original density, fx, is just 1 on lambda e to the minus x on lambda. That's just the density of an exponential function. And then h is invertible for all x greater than 0, and the inverse of h is just the square root, right? So then since x is equal to the square root of y, the corresponding derivative is just half of the inverse of the square root of y. And then performing the relevant substitutions, we get the formula for the density of y in terms of y. Okay, and then remember what I said. Remember my first tip was that always specify the domain. So in this case, since x is always positive and y is x squared, then y is also always positive too. Okay, and then we have another example here. So if x is uniform between minus 10 to 10, what's the density of y is equaling to x squared? So to get this, it's the same steps as before, but then notice here, x is bounded between negative 10 to 10, but since y is x squared, y is bounded between 0 and 100. And notice that y is not a uniform distribution anymore because we have this square root factor here. Okay, so now this next example looks at the joint probability distribution. So as I mentioned before, right, when you're doing a joint probability distribution question, the question will give you a table of values. So then let's look at this. So we want to calculate these probabilities. So the probability of x equaling to 0 and y equaling to 1. So you just look at the table, right? X equal to 0, y is equal to 1 over 8. Probability of x being greater than or equal to 1, y being less than 1. So if x is greater or equal to 1, it's either in this row or this row. And if we want y less than 1, it has to be in this column, right? So it's just 1 on 8 plus 3 on 16. And then the probability of the difference between x and y equaling to 1. So there are two possible cases, x is equal to 2, y is equal to 1, or x is equal to 1, y is equal to 0. So x is equal to 2, y is equal to 1 over 4. X is equal to 1, y is equal to 0, 1 over 8, and you just take the sum. Okay, so we have another joint distribution question. So in this case, we have this density function, this joint density function, and we want to calculate these two values. So probability of x being less than 2 and y being greater than or equal to 4. So recall that for a joint density function, to evaluate probabilities, we look at the double integral. So in this case, y ranges between 4 and infinity, and x ranges between 1 and 2, right? Because x is greater than or equal to 1, but x is less than 2. Y is greater than or equal to 4, and then y is also greater than or equal to 1. So in this case, it's between 4 and infinity for y, and 1 and 2 for x. And then evaluating this, we get 1 over 8. Okay, and then this next one, it's slightly different, right? Because now we're not necessarily bounding by values, we're bounding y by x. So if x is, maybe the sign, I think the sign is switched around here. There should be a greater than equal to sign. But anyway, since y is positive, we don't necessarily have to worry about the plus or minus, right? Since the random variables are all positive. So in this case, y goes between 1 and x squared, and then x goes between 1 and infinity. So I think there might be a couple typos in this question, but the general idea is still the same. Okay, so in this case, we have this another table, and we're trying to calculate the expectation of this joint function. And then remember, the way of calculating is still the same. We look at the corresponding value, and then the probability of that particular outcome. So in this case, right, y can equal to 1 or 2, x equals 1 or 2. So in this case, if they're both 1, if one of them is 2, one of them is 1, if one of them swap around, and then if they're both 2, and then in each case we multiply the corresponding probability. And then, yeah, we just get that. And then examine the existence of the expectation of the product for this example which we looked at earlier. That's something that you can work on, but I think we'll talk about this in a sec. Let me have a look. Yeah, so we talked about it here. Let me check. Okay, yeah. So we're gonna go back to that now. So then, this next example is like checking if this joint distribution is independent. And then recall that the joint distribution is independent if it's equal to the probability, to the product of the probability of the marginal distributions. So in this case, fxx is just equaling, so to get the marginal distribution x from the joint distribution, we integrate over all the y values. So we integrate from 1 to infinity since y is lower bounded by 1, and then we get this. And then similarly, I notice here that I specified, oops, I'm trying to highlight this part here, but it's not showing. So notice that after I calculate fxx, I specify that x has to be greater than or equal to 1 here, same idea here. And in this case, since the joint distribution, or the joint density, is equal to the product of the densities, then x and y are indeed independent. Next up, this time it's a bit different. This is not necessarily a joint distribution, this is a conditional distribution now, and then the way we use the table will be a bit different. So notice that to calculate the probability of y, hang on. Okay, so for example, right, the probability of y equaling to 2 is equal to the probability of x equaling to 1 and y equaling to 2 plus the probability of x equaling to 2, given that y and y equaling to 2. So this first one, right, hang on, give me a second. Okay, yeah, so the probability of getting y equaling to 2 is just 3 over 5, because it's just this plus this. And then to calculate the conditional probabilities now, we use the formula from before, so it's just x equaling to 1 and y equaling to 2 divided by probability of y equaling to 2, so that's just, so for example, right, to calculate the probability of x equaling to 1, given that y is equal to 2, we divide by the probability of y equaling to 2. Because if remember, in the Venn diagram, right, all we're doing is we're restricting ourselves to the circle corresponding to y equaling to 2. Okay, and then now we have the same joint density function again, except this time we're going to prove that x and y independent using this result here. And then, actually, this will be left as an exercise for the listener. Okay, and then, okay, so this next question, we're calculating the expectation the conditional expectation. So in this case, it's the same idea, but notice that when we're weighting by the probabilities, we don't get the values directly from the table anymore. So for example, right, the probability of x equaling to 1, given that y is equal to 2, so when we're already in this column, the probability that x equals 1 is not 1 over 5, it's 1 over 3. Because when we're in this column, this is only half as likely to occur as the other possible value for x. Yeah, and okay, so that's just for the expectation. And then to calculate the expectation of x squared, the probabilities are still the same, but the outputs are squared. And then the reason we calculate this is because for this question, we also want to calculate the variance. And I think this should just be x. So this is a typo here, but then it's just 3 minus this. Okay, so for this question, we're calculating the covariance. Okay, and then we have this distribution here. And the question, for some reason, asks us to calculate it in the old-fashioned way. So the way you would do this then is to first get the marginal densities. So remember, to get the marginal density, you integrate over all the values for the other random variable. So in this case, to get the marginal density of x, we integrate the joint density over all the possible y values. And since y is bounded between 0 and 2, that's how we get this. Okay, and then we calculate the expectations after we've obtained the corresponding marginal densities. And then we calculate the expectation of the product by looking at the corresponding double integral. And then finally, you'd plug it into the covariance formula for x and y. But an alternative method in this case is if you can prove that x and y are independent, then you can just directly take the product of the expectations. And then, yeah. Okay, we have another question here. So now we're trying to prove that the covariance of x and z is 0. So z is a normal distribution, standard normal distribution rather. W is this random variable, very interesting one here. So probability of x equaling to 1 is half, probability of x equaling to -1 is half. And then suppose that w and z are independent, and we define this new random variable x, which is the product of w and z. So we're trying to show that the covariance of this new random variable and the standard normal distribution is equal to 0. So all we do is we start off with we just write down the formula, right? So remember, this is not the definition of covariance, but this was the alternative formula, which is often easier to work with. And then note from the question that since EZ is equal to 0, right, because the mean of a standard normal distribution is 0, then this part here is just the first part, because this part disappears. Okay, and then subbing in x equaling w0, we get this. And then since the w and z are independent, we can split this expectation up into the product of two different expectations. And then we can just calculate the expectations and then get 0. Because the expectation of w, right, is 0, because it's 1 times half minus 1 times half. Let's look at this next point. So then this next example deals with the bivariate transform formula. So that was the one involving the determinant of the Jacobian. And then this is just the example that's taken from Lieber's notes, I believe. So then if x and y are both IID as exponential with parameter 4, find the joint density of u and v if u is defined as this and v is equal to y. Okay, so then we have y is equal to v, and then u is this. Rearranging to get x, we get x is equal to 2u plus v. And then finding the Jacobian matrix, we get this. Remember, so the Jacobian was just dx du, dx dv, dy du, dy dv. And then the determinant of this matrix is just 2. Okay, so then this is the joint distribution. And then since y is equal to v and x is equal to 2u plus v, we just make the substitutions and then we multiply by this factor here to get this final value here. Next up. Okay, and then yeah, so this last part, remember whenever we get a new distribution function or density function rather, we have to specify its domain. So we know that y has to be greater than 0 since it's an exponential distribution, and since v is equal to y, v is greater than 0 too. And then x is greater than 0, and since u has this relationship with x and v, we get u has to be greater than minus v over 2. Okay, in this case, we're using the convolution formula now to find the sum of x and y. So x and y are both IID to the geometric distribution. So then the corresponding probability function of the geometric distribution, it has this formula. We've seen this before. Same thing for y. And then this part here, this is just like the reason we're looking at the probability of x equaling to z minus y is simply because that's like the formula that we need to calculate the convolution. Okay, and then we'll notice here that z minus y, y minus z has these values, so then y has these values, and the other way around. And then look here. Give me a second. Okay, so then this is just what we had from before, and then this is just subbing in the probability function for y, and then we get this expression here. And then this part here is just we're getting the range of y in terms of z, because for the convolution, what we're doing is we're summing up the probability function of x equaling to z minus y multiplied by the probability function of y, and we're summing it over all the possible y values. And notice that the sum only depends on y. Okay, and then this is like the actual like formula, and then this part here is just talking about the domain. So this next example, so it's another convolution example, except in this case we're dealing with a continuous random variable. So then for the continuous case, we're interested in these two quantities. So fx z minus y, fy of y, and then fx z minus y is just equal to this, because the density of fx is just this, and then fy, yeah, it's just e to the minus y, but then since we're multiplying these two, the y in the exponents cancel out, and we're just left with e to the minus z. And then looking at the corresponding domain, we get y being bounded between 0 and z. And then once again, to actually get the convolution, we just integrate it over all the possible z values, and then, or rather all the possible y values, and in this case, y is bounded between 0 and z. Okay, and then the question asks us to prove that this follows a gamma distribution of parameters 2 and 1. So after we evaluate the integral, we only get this. Whoops, I didn't mean to highlight. I meant to highlight the middle part. But then we can easily show that this middle part is indeed equal to this, which is the density of a gamma 2, 1 random variable. Okay, so then this next example. Okay, so this next example, I think, is it the same question? Yeah, it's the same question, except this time we're using the moment generating function approach. So recall that the moment generating function of the sum is equal to the product of the moment generating functions. So in this case, we have this, and then this here is indeed the moment generating function of a gamma 2, 1 distribution. And from there, we can directly conclude that z has this distribution then. Yeah, so then I'll be right back in a minute, sorry. Okay, so sorry about that. So the previous questions were mostly just like computation questions. There wasn't too much to it. It was simply like recognizing which formula you had to use, obtaining the relevant quantities and expressions, and then just subbing it in. These next set of questions will be a bit more complicated in the sense that we're looking at the limits now. So these limit questions, it's not just like computing stuff, it's actually like proving stuff. So let's have a look at this question. So we have the sequence of IID uniform 0, 1 variables, random variables, and then we define our new random variable to be n times the minimum of, I think, of these uniform random variables, and then prove that y converges in distribution to y, where y is distributed as an exponential function of parameter 1. Okay, so to do this, we look at the CDF of yn, and by definition, it's just the probability of yn being less than or equal to y. And then given the definition of y, it's just this. And then dividing both sides by n, it's this. And then taking the complement, we have this. And then we have a couple of observations here. So in general, if the minimum of the set of x values is less than or equal to x, then not every x value is less than or equal to a particular x. But rather, if the minimum of these is greater than x, then of course every x value is greater than or equal to x. So that's why we took the complement to reverse the sign of the inequality. And then since these are independent and identically distributed, we can split up this into this, because the probability of the minimum being greater than some value is just the probability of each random variable being greater than that value, right? Okay, and then from here, so then from the independence part, we can split up this probability into the product of the different probabilities. And then since these are all identically distributed, we can like group these products together into a single exponent. And then since u is just, and then to actually evaluate this then, we need u to be between y over n and 1, because I remember each of these are uniform 0 to 1. So this is only greater than y on n if it's between y on n and 1. And then we get this. But then what does this say? Well, what this says is, but then if we take the limit, right? So remember, we're looking at the convergence and distribution. So then if we take the limit as n approaches infinity, notice that this part here just becomes e to the negative y. So what we've shown then, and this is indeed the CDF for an exponential of 1. Exponential distribution of parameter 1, rather. So hence we can conclude that yn converges in distribution to y. So let's just reflect on this question for a bit. So in this question, we used a few tips, a few tricks, right? So to start off with, we isolated this minimum factor by dividing both sides by n, and then what we did is we took the complement to flip the sign of the inequality, because since we're dealing with the minimum, having the minimum greater than or equal to a value is more useful than having the minimum being less than a particular value. And then by definition, this is just equal to this. And then using the IID part, we can first split it since it's independent, and then we can group it together since they're identically distributed. And yeah. Any questions about this problem? There are no questions, we'll move on, because we see that these problems are starting to get more and more involved, I guess. Okay, so let's look at this next question. Australians have an average weight of around 68 kilos and variance around 16 kilograms squared. So remember, the variance is not in the same units as the random variable of interest. It's in the units squared. Suppose 40 random Australians are chosen. What is the approximate probability that the average weight of these Australians is over 80? So then, notice that this question, right, it doesn't tell you to use the central limit theorem, right? But then we know that since we have a group of IIDs, right? So if we let each random variable be the weight of an Australian, we have a set of IIDs, and we know that we can model this using the central limit theorem, because we know that by the central limit theorem, if we normalize our random variable, then we know that it converges in distribution to the normal random variable, to the standard normal distribution. Okay, and then from there, to perform the necessary calculations, then we want this quantity to be greater than 80, right? So what this quantity is, this is like the average weight, right? So for this to be greater than 80, we want, so then performing like the same manipulations on both sides. So to go from here to here, so from this first part to the second part, it's just doing the same algebraic manipulation on both sides, so we're not changing anything. But the reason we do this is because we know that this converges in distribution to a standard normal distribution. So then after we do that, we can replace this part with z, and then from here, well, for you guys, you'll just be looking at the table of values. Okay, and then, okay, so now, wait, actually, before we move on, any questions about this example? So just to quickly recap, right, this question, we had to recognize that we should be using the central limit theorem, right? Because we had a group of these 40 independent and identical random variables with the same mean and variance. And then it was a matter of like converting this 80 into this quantity here, because we knew that this quantity on this side could be modeled by a standard normal distribution. And then from here, you just like look at the table of values. Okay, cool. This next example, so an unfortunate soul decided to sit his exams despite having a migraine and the flu. Fortunately, it was not a university exam, and the paper involved only 200 multiple choice questions with 5 options. Therefore, he randomly guesses every answer. What is the approximate probability he fails? So I hope this isn't like any of you guys. But anyway, so x is distributed as a binomial distribution with parameters 200 and 1 over 5. So 200 here is the number of trials. In this case, it's the 200 questions. And 1 over 5 here is like the probability of success. So given that he's just randomly guessing and each question has 5 options, it's just 1 over 5. Okay, and then this part here is important. So how did we get this? Well, remember, we had the application of the central limit theorem in that we can approximate a binomial distribution by a normal distribution. So in this case, the probability of x being less than 100 is approximately equal to the probability of y being 100, or y being less than 100. So remember, the way we got this is simply by applying the I think I have it here. So it's just this result here. Oops, not yeah, this result here. Okay, and then from there it's the same idea. So then we convert y into a standard normal distribution. So to get to standardized y, we subtract the mean and divide by the standard deviation. But then if we do that to y, we have to do it to the right hand side as well. So that's what we do. And then simplifying it, we have this. And then, okay, so then if you actually look at your table, the probability of the person failing is pretty much 100% at this point. Okay, cool. So then next example, we have a sequence of IIDs with mean 2 and variance 7. Obtain a large sample approximation for the distribution of xn cubed. So in this case, remember, so part of the difficulty in a question is like figuring out which result you're meant to be using. So in this case, we're given a sequence of IIDs, of IID random variables, with the same mean and variance, and then what we want is the distribution of the transformation of these random variables. So then, if you're familiar with the delta method, then that's what should like be ringing in your head right now. So we'll be using the delta method, but first of all, before we use the delta method, we use the central limit theorem first. And this is just a variation of the central limit theorem. So then notice that we're looking at the mean, so then we're subtracting 2, which is the mean. And then we have this square root of n here, because that's just like the formula in this case. And it converges in distribution to a normal distribution with mean 0, since we like normalized for that already. And then variance 7, right? That's just from the question. And then applying the delta method. So the delta method, we have this g function, which is the transformation which we apply onto the random variable. So in this case, we're looking for x cubed. So gx is just x cubed, and then g dash x is just 3x squared. And then subbing in the relevant stuff for the delta method. So how do I get this? Well, it's just like looking at the formula, and then subbing in the relevant values, we get this. Okay, and then simplifying this, we get this. So then, and then moving everything, and then I guess like, we're like undoing the normalization, I guess, by like, for example, right, as we're undoing the normalization in the sense that if x, so oops, the formatting is a bit off here, but since the x cubed minus 8 has mean 0, so then if we just isolate x cubed, then the corresponding normal distribution will have mean 8. And since we are multiplying by square root of n here, the corresponding normal distribution, if we isolate this, will just have variance 1008 divided by n. So it's just like isolating x cubed of n by itself. So then let's just quickly recap this question. So this question we used the delta method because we had a sequence of IIDs and we're looking at the distribution of a transformation of a random variable. So then what we did was we used the central limit theorem first of all to give us the distribution of the sample, and then we applied the delta method using gx equals x cubed to get this result here. And then we simplified to get this, and then we like undid the normalization, I guess, to get x cubed by itself, and then we get the corresponding changes in parameters. Any questions about that? Okay, no. Okay, so we'll look at this next example then. So the Riemann-Zeta function is defined for complex S of real part greater than 1 by the absolutely convergent infinite series for this, obviously. And then we want to prove that the real part of every non-trivial zero of the Riemann-Zeta function is half. Okay, so then it's not too hard. So then, yeah, so this is the proof. Anyway, so that last example was a joke. We're pretty much done for today. So just to quickly recap, what we looked at today was we reviewed the relevant theory of what you needed to know, and then we went through various examples. And then remember, the most important part for today is knowing how to do the relevant computations for like the bivariate. So someone asked me if I could explain 29 again later. Yep, sure, I'll explain after. Yeah, I'll explain in a sec. Okay, so then the most important part for today is knowing how to do the relevant computations. So if you remember from the first half of those examples, it was just a lot of computations, and you need to be familiar with how to do each type of computation. And then also, you need to know how to work with the limits. So the limits part is probably the most confusing, but if you look back at the limits, there's only like 6 or 7 things that you need to know. You only need to know these 3 modes of convergence. You need to know the central limit theorem. So the central limit theorem has like different formulations, and you should be familiar with each one. You need to know the weak and strong law of large numbers, the difference between each one, and you should know the statement and know how to use the delta method. So I'll go through example 29 again, but before we do that, let's just quickly review like the delta method then. So then this is like the definition, I guess, of the delta method. And remember, there are different ways of stating it. But then the idea is that if we have a sequence of random variables such that yn minus the mean divided by sigma multiplied by the square root of n converges in distribution to a standard normal distribution, then we have this. So notice that this is slightly different to what we had in the question, because in the question we didn't have the sigma in the bottom. Rather, we had we saw that this top part converged in distribution to a normal distribution with mean 0 and variance sigma squared. So remember, there are like a lot of different ways of formulating like the central limit theorem and the delta method. But the idea is that if we don't subtract this part, say the minus theta, then the normal distribution would have mean theta. And if we don't divide by this factor sigma, the normal distribution would have variance sigma squared. So it's like a lot of equivalent ones, and then in that example 29, we established this part using the central limit theorem, and then from there we applied the delta method. So then what the delta method says is that if we have this, then we have this. Okay, so then this is what we had before, right? So remember, theta was the mean, g was just cube. So then we had xn cubed minus 2 cubed, and then the top square root of n, and then we had sigma squared g dash theta squared. So we'll look back at the question and see that's exactly what we had. So let's just go back to that question. Okay, so I think I forgot to say this earlier, right? But the reason we're dealing with x bar n is because what we have is a sequence x1, x2, ... But then to use the central limit theorem, we have to look at the mean of these random variables. So then we know that the mean of these random variables, if you subtract by 2 and then divide by square root of n, converges in distribution to a normal distribution with mean 0 and variance 7. So this first part here is simply applying the central limit theorem, or one of its formulations, onto this like set of IID variables. So that was the first part. And then we apply the delta method with g equaling to x cubed, and we get g dash equals 3x squared. So let's look at what happened here. So look, this is what we had before, right? So we had the square root of n. This is gx, right? So then x cubed, right? And then this is g of 2, which is just 2 cubed. And we know that this converges in distribution to this part here. So then this 3 times 2 squared is the g dash theta squared. Because if we look back at the, let me just go back to the formula. So look, so that was just the sigma squared and then g dash theta squared. So then, I guess the tricky part of this question was knowing how to apply the central limit theorem, because applying the delta method, it's simply recognizing that the transformation is cubing it, and then you're just subbing in the appropriate values into the corresponding formula. And then we can just simplify this by doing like the reverse mapping, right? So if I'm minusing 8, I can plus 8 to I can undo this minus 8 to have the mean being 8. And if I'm like timesing by the square root of n, I can like get rid of this part by dividing the variance by the square of that. Does that make sense? Yeah, so we're like discarding like all of the stuff on this side because we only care about the distribution of this particular part. But then we can't just like chuck this away and not change this part, right? If we chuck away this 8, then the normal gets shifted by this much. If we undo the scaling by root n, then the normal gets scaled by this much. Yep, you're welcome. Any other questions? So I just wait like a couple minutes to see if anyone has any questions. So so these slides are available, and I think if you look up in the chat, the StatSoc account did post a link to these slides. Yeah, so thank you, Faker. Yeah, so the only reason I stopped playing like professionally for League is so I could help you guys with your 2901 exam. Yeah, so I'll just be like hanging around for a couple more minutes if anyone's any questions, but otherwise, that's it for today's revision seminar. So don't forget, tomorrow we'll be hosting part 2 of the revision seminar, which is on the statistics part of the course. So I believe Henry from Mathsoc will be doing the revision seminar tomorrow. I'm only doing today's one. Yeah, you're welcome. Okay, so if no one has any questions, we'll be ending the stream shortly. So this is like a last call for questions. Okay, cool. So we'll look to end the stream now then. Thank you everyone for coming, and good luck for your exams. Hope to see you all tomorrow at the statistics part of the revision seminar.